Now we're going to talk about a very, very important concept called non-singularity. So, definition. A matrix is called non-singular if for each B, that is augmentation B, the system A augmented with B has a unique solution we will say, or we shall say, that A is singular otherwise. So singular in this context actually roughly means unusual, right? So this matrix is actually kind of unusual. It's more likely, in some sense, that can be defined rigorously, that this does have a solution, a unique solution all the time, under certain conditions, of course. So we have a fact about non-singular matrices, and it's really related to the having at most one solution and having at least one solution, those facts that we've derived already. And this kind of completes all the questions that we had about solution sets of particular matrix equations. So fact. A coefficient matrix is non-singular if and only if the number of rows of A is equal to the number of columns of A is equal to the rank of A. That's the only time that occurs. And if that happens, then you have non-singularity, which is the same thing as having a unique solution for any augmentation. So let's prove this fact. And with our previous facts, this is actually really quick proof. So proof. So row of A equal to rank of A is equivalent so this if and only if is similar to is the same thing as actually equivalence, right? So the equivalence of statements. So this is true is equivalent to this is true, right? So by our fact, rank A equals row of A is equivalent to existence of at least one solution to AB for any B, and the number of columns of A equals the rank A is equivalent by our other fact to at most one solution. So there's at most one solution to A augmented with B for any B. So we can just combine equivalences. So taking the conjunction, we have that row A equals col A equals rank A. is equivalent to row of A is equal to rank A and column of A is equal to rank A. So this statement is equivalent to the statement that there exists a solution and it's the only one. That is, it's the unique solution to there is a unique solution to A, B for any B. But that was just the definition of non-singularity, and so we have the proof. We have the equivalence of these two statements, and we're done. We write our tombstone. Now, what are some interesting kind of consequences of this, right? So one thing is that, well, if we have a non-singular matrix, the only way it could even possibly begin to be a non-singular is that we have to have that non-singular, well, a necessary condition to non-singularity, right? We have to have that call A is equal to row of A for non-singular matrices. And for matrices like this, we call these square matrices. So square matrices, right? Because they don't look like rectangles, they look like squares. Now, for a given square matrix, determining if it's non-singular amounts to seeing if the matrix has maximal rank, right? So the rank cannot exceed the number of columns or the number of rows, and so the maximum is col A and row A. And we say that if this equality, if the rank is equal to these two numbers, then we say that it has maximal rank. So if rank A is equal to col A is equal to row A, then A has maximal rank. And this is a very important problem in linear algebra, is determining if A has maximal rank, right?